Hello, everybody, and welcome to this webinar. My name is Marius Gatzen. I'm Senior Project Manager of Simufact Engineering in Hamburg, and I'm mainly responsible for our software Simufact Welding, which is a solution for structural welding simulation. The title of this webinar is Simufact Welding, Live and in Color, a German phrase, how it works. And this webinar is actually the third episode of our webinar series about structural welding simulation with Simufact and MC products. If you have attended the last two webinars, you have already learned the concept of structural welding simulations, the benefits of using structural welding simulation for production planning, and how the Simufact welding product can be used in a broader scale of production planning. Today, we are going to really look at the software itself. What is Simufact Welding in particular? And we will kind of doing a quick tutorial. So we will really dig into the software itself. We are going to present you the look and feel and how easy it is to really set up structural welding simulation with this tool. Okay, so then let's start with the presentation. Simufact Welding, structural welding simulation for thermal joining processes. This sentence essentially says everything about what Simufact Welding really is and also what it not is, because although these type of simulations are usually termed welding simulation, you have to distinguish between certain aspects of welding process and what part of it is really going to be simulated with a structural welding simulation. To put this in perspective, let's look at the typical phenomena of thermal joining processes, the challenges and the hurdles that a usual welding engineer has to overcome in his daily work. You could separate them into three different areas. The first one is really the process zone or the process itself. It has everything to do with how really the energy of the energy source is put into the material, how the process is made stable, how you handle melt pool movements, instabilities like spatters, and in general, how you achieve a good seam quality, for instance, avoid pores, and when we're talking about brazing, for instance, to get good wetting and so on. And then the next area is metallurgical effects. So the welding engineer has to take care of all the phase transformations that can occur. He has to consider hardening and softening. And since most welding applications are using additional material, you also have to consider all the local change of chemical composition. So this can be termed as the weldability, basically. And then there is the third aspect of, or the third area of welding phenomena, which are the structural effects. And this has everything to do with basically the shape and the quality of the product, the end product, the net shape of the assembly that you want to get. So you have to consider deformations due to thermal irritation. You have to consider gaps that may open during welding, the entire complex of residual stresses, and you also have to consider all your peripheral objects like the clamping system in general, because this has also a huge impact on the final deformation. So one could argue, and this is also an ongoing discussion for 30 years now, that everything needs to be combined in one welding simulation. But in fact, because all of these different physical processes take place on very different timescales, for instance, the process has very high velocities and it takes place on very small time scales, while the structural effects are usually take place on much higher time scales. It doesn't really make sense to make a fully integrated and combined simulation. So what people do is basically reduce the model to what they really want to look at. And this is why welding simulation can be separated into, let's say, process simulation and structural simulation. Simufact Welding really is a solution for the structural simulation. So we look at everything that has to do with residual stresses, with strains and deformations that take place during welding, during non-linear heat input, and really look at the net shape or the final shape of a structure and after several weld lines and so on. What is Simufact Welding in particular? Well, Simufact Welding, the product, if you want, is really a front end or a GUI solution. Simufact Engineering is very successful in the last 25 plus years in creating very user-friendly GUIs that are very reduced to really have only functions that an engineer, not an FE engineer, a welding engineer or a forming engineer really can use. So it uses also the wording from the welding community instead of the FE community. And it is really a solution that makes it easy for you to look at an FE model from the perspective of a practitioner. And and this is really what it is made of. It consists of a process tree where you can organize all your processes. Processes refers to model. We call them processes, and the entire Simufact and they are gathered in what we call a project. And then the next thing you have is an object catalog where you organize all your entities, your geometries that you want to assemble together, your weld line information, and also your material definitions. And then we have a model view that is used for pre-processing, and we have a result view that gives you access to the results once you have the first increment modeled or simulated. And it is all done in all-in-one GUI solution. The only part of the calculation that you don't see is really the calculation itself, the solver itself. So it is hidden from you because we want to avoid anything that is too much into detail, but of course it is completely transparent. The first layer of the GUI that you see is completely user-friendly, but it is also open. If you want to dig deeper, then you have a second layer and a third layer behind it. I think next week we will also have a look into this, and you can essentially access every aspect of also the FE specific terms that you want to change. Simufact Welding is also designed that you can follow a certain workflow. You don't have to follow it, but it makes pretty much sense to follow this workflow. First of all, you set up your geometries. And the next step, you define your weld lines. You can do this in our GUI either by clicking on edges and define certain edges as being weld lines, but you can also import CSV files, or you can also import NC code like G code if you have them. And the next step is really to add fixture, the entire clamping system. Then you have to put in what is called equivalent heat sources, which are basically the representation of the process itself. As I said before, structural welding simulation is not really a process simulation. So the welding process itself is taken care of by using so-called equivalent heat sources, which basically represent the heat input. Then the next thing you have to consider is material model. Of course, since we are dealing with nonlinear material behavior in this case, you need to add a lot of, you have to specify a lot of material properties. Luckily, Simufact Welding comes with a fairly big database, but we are also able to use third-party generated material models in our GUI. And then basically the model is set up, you give it over to the solver, and once you have your first increment, you get the results. So now I want to show you how this is really conducted in the software on the basis of a real-life example from a customer in the Americas. They had struggle with the suspension arm. They wanted to create a suspension arm which is assembled basically from a corpus and a reinforcement plate, and they put in a lot of very long weld lines along here and along here, and everyone that has to do with welding would already know that this would result in shrinkage, and in this case, this entire assembly shrinks in a way that you get a very critical deformation here at the tip of this pin. And if you would assemble this one into a car, you would get a lot of noise. So they wanted to get rid of it, and they didn't really find a solution on a traditional way. So they approached us and asked us if we can help them. And of course, we can help them because we provide a virtual test facility where you also can do some sorts of silly ideas before you really do them in your workshop and waste material. And one thing they wanted to test here is, what about pre-bending? So this is a very not unique, but it is not very often the case that these type. But in this case, this was one of the variants that they asked us to test, and then they welded it again, and they actually saw an improvement in deformation. And I want to show you in the next few minutes, let's say 20 minutes, how to set up this kind of model to get from the input data, which are basically a meshed CAD data, to this sort of improved deformation. And to do this, we go into the software itself. So here you see Simufact Welding, the product itself. It has here the process tree, object catalog, and here is the result view of the model that we just put up and calculated. This is the result. You see the critical deformation in front here. This mesh here is the original shape, and you see that there is a lot of deformation happening. And when is it happening? It is basically happening during cooling. You can see this, start the animation. You see that this process was conducted with 2 robots, actually. So it was welded on both sides simultaneously. And actually, nothing really bad happens during welding itself, but most of the deformation really happens after the welding has finished and the part is cooling. So here you see it. So how do we get to this kind of simulation? This is what I'm going to show you. In order to set up such kind of simulation in Simufact Welding, we simply create a new process. When we want to create a new process, this process settings window will pop up, and you can choose between different process types. Process types means basically presets for the GUI as well as for the solver. And we can choose between different thermal joining processes: arc welding, laser welding, electron beam welding, and brazing. And these are the 4 thermal joining processes. And we also have an additional module for resistance spot welding. And since January this year, we also have a dedicated direct energy deposition module, which approaches the solver a little bit different than the usual welding application, which considers basically 3D printing with a robot, everything that has to do with deposition welding. Then we have a very specific process type called stress relief heat treatment, which is essentially putting your part, your just welded part, in an oven and let the stress relieve. And we have also the special process which is called cooling and clamping, which is actually not really a welding application, but only an in-between mode if you simply want to model clamping and unclamping and such things. Okay, you can conduct a lot of presets. For instance, tell the GUI how many components you want. These are kind of presets, and you already see that we have broken down everything into entities or model objects. So you have the components, then you have all sorts of boundary conditions, which we try to name, not really in an FE style, but more in a welding engineer style. For instance, a bearing and a clamping, and this is actually what they are. And we have a robot object that takes care of all the of the welding process, which organizes the heat input, the weld lines, and also the creation of weld seam reinforcement. In this particular case, I want to go with 1 fixed geometry because the boundary condition is quite simple in this example. And we are going to use 2 robots because this was a tandem process. And then you get a preset model that has empty model objects with it that you can fill up now. So the first thing, if you remember our workflow or recommended workflow, is that we need to define our geometries. And we can simply take them from the object catalog, drag and drop them onto the process, and then for each of these separate meshes and a separate component entity is created, which contains all the information about this particular body. Then the next thing in the workflow we need to do is define the weld lines where we want to join the parts together. And to do this, you simply make a right mouse click at the robot, and then in this case, I will choose the. I will simply pick an edge from here to here, and then it will take every node of the mesh in this line along this edge, and they will all be what is called trajectory points. And this thing is then also called trajectory, which is basically a weld line. And then I want to have another weld line here to here. And then they are in the model. And actually, I also want to weld along this side, but here I'm going to simply drag and drop them onto the second robot. And then I have my weld lines defined. You see that they consist of red dots, which are trajectory points, and they also have these black arrow, which is the alignment of each particular trajectory point, and it points into the direction of the heat source, for instance, a laser. So it would point into the direction of the laser. Okay, so the next thing we want to do if we follow our workflow is to create boundary conditions. In this case, it is pretty easy. We have only one fixed geometry. This entire assembly shall be fixed here in the room by just attaching a small geometry to this corpus. And I have already a fixed geometry entity in my model, but I don't have a geometry right now. I don't have any CAD data for it, so I can simply create it in Simufact Welding. Very basic shapes. So I can choose between a cylinder and a cuboid. In this case, I want to take a cylinder, and then I can simply pick a location, point, drag, and then I have a surface meshed body that is attached perfectly to the surface here and serves as boundary condition. So the next thing we need to do is align and adjust the weld lines. And also in most cases that I've seen in the past, the weld reinforcement, because we're dealing here with an arc welding process, the weld reinforcement or the weld seam itself is usually not part of the CAD data. Hence, you don't really have a mesh geometry of them. And since they add up to the stiffness, you need to model them here. So you also have to have a mesh for them. And if you don't have the mesh here, just the weld lines, we have a tool which is called weld bead generation to simply create them along the weld line. And to do this, first we have to align the geometries, and therefore we go into the first robot object, we go to trajectories and align them around certain areas. So in this case, we want to align them to the right part, give it a slight offset, and then it's aligned, and then we want to generate a weld bead on top of this. You can either create a preview or you can simply create it directly. And then you have these bluish colored geometries that are added into the model. And they are colored in blue because they are organized over the robot element, and they are treated in a special way later in the simulation because they are not, although you have to define them prior to the simulation, they are not initially in the model. They will add up later when the heat source is propagating over the trajectories and actually perform the joining. Let's do this also for the other component, for the other robot. Here, and the last one. So this is really a very powerful tool because it's basically using a triangular shaped cross section, and then you extrude them along the weld line, and it will also adjust a little bit. If you have gaps that will open, or if the inclination of adjacent wall will change, it will also try to fit. Of course, there are also extremes where it doesn't work, and then you have to adjust it manually a little bit. But it's a very, very robust tool. Okay, so the next thing is really taking care of the heat input itself. For this webinar, I'm going to simply add a heat source, or how we call them, welding perimeter, and just give you a visual imagination of how they look like, because modeling welding parameter, I think, is a little bit advanced and would be a little bit too much for this webinar. But basically, what they are three-dimensional representations of the heat input, and they usually look like the melt pool. So this is actually what happens here in the model, in this structural welding model. When you start the animation, this is just a pre-animation. You really have a heat source element or a heat source geometry that propagates along a predefined geometry. And during its propagation, it will evoke these bluish elements, which are the weld seam or weld reinforcement, and will both apply energy and heat to the entire structure and will also add material. All right. You see that these containers here have different colors. The fixed geometry has actually turned from red color to black color, which means all information, that it has all informations. Red means there is still information missing in order to be able to start the simulation. And of course, for our components, as well as also for the welding material, we need to add a material definition. And this can also be put into the model either separate for each individual container, but you can also drag and drop it on the process definition itself, and then it will be forwarded to every sub-element. And of course, we also need to add thermal boundary conditions. And then basically everything except for the process parameter here on the bottom is set. The components here had turned their color from red to yellow. Yellow means basically there is an additional information, or you can call it a warning, but it is essentially able to be run. So if you don't know what is missing, you can also go into our model check. It will give you errors and warnings, and errors are the things that you need to fix, but warnings you can, in particular cases, ignore. And in this case, we ignore it. So the error says end time of analysis is 0 seconds because we don't have added any welding time or analysis time yet. And this is what we do here. First, let's let this run on 4 cores, and then we set an end time of, let's say, 120 seconds. When we look at those robots, the first robot has a total runtime of 28 seconds. The second one has a runtime of 32 seconds, and they both start immediately after starting the simulation. So basically, we are simulating here about 30 seconds of welding, and the rest is cooling. And this is very important because most of the deformations actually happen during cooling, which is the case in most welding activities. All right, so this model is then completely set up, and we can press start because we have ignored the warning. The model check will tell us that there are still warnings. In this case, I used a multi-phase material, but I didn't set an initial phase composition of each component. But that doesn't matter for the purpose of this webinar. So I'm going to continue. And then basically the simulation starts. Now, here's the point for those of you that have already done structural welding simulations. They are very complex, transient, thermomechanically coupled nonlinear simulations. So this is nothing that runs in a couple of minutes. So this particular model here actually runs for about 4 hours. And this is due to the fact that the sheer size of the model. Usually welding simulations contain a lot of component, or at least this is what our customers would like to simulate. No one wants to simulate 2 sheets welded together. They wanted to do entire assemblies like a door of a car or something like this. And you also have to subdivide your simulation in very small time steps. Because as you already saw here, you have moving heat sources, and you have to make sure that you have a certain overlap between each time step when these heat sources are moving. And this is mainly the fact why welding simulations take much longer than, let's say, crash simulations or normal linear mechanical analysis. All right. So at this point, I'm going to stop the simulation because I'm actually doing this presentation only on my small laptop at the moment. But let's hop back to the result that we already saw this year. So we have now set up this model entirely, and this is what it would look like if we would have 4 hours time. And I wanted to point out something, because what I just set up is not the entire story. It was actually a little bit more, let's say, complicated. No, not really complicated, but it was made in different steps. Because when I hop back to the beginning of this animation, you see that you already have residual temperature here around the pin and the tube. And this is due to the fact that this simulation is actually the second the second step of the assembly process. The first step is really only welding the pin, the cap, and the tube to this corpus. And it's essentially set up in the same manner. So you create weld lines along the edges you want to join together, and then define your heat sources, define your material, and you're good to go. And the good thing about Simufact Welding is that you can use the result of this particular model to add additional parts and to simulate the next step. To do this, you take the result of the first step and create a copy from result. And this will essentially automatically create a new model completely set up, but in the shape and also with results for each component from the previous step. And now you can add up additional parts like the reinforcement plate. So we simply add in a new component container, and then we put in the reinforcement plate from the other example that I just showed you. And in some cases, here it is not that problematic, but in some cases, of course, you add ideal CAD shaped geometries to an already deformed geometry. And you may run into the problem that they don't really fit into each other. And there are two things that you can do. The first thing is you can simply take your new geometry and position it in a certain way and try to make it fit. We even have what is called a gravity positioner, so it will kind of drop into the geometry. This is a very small two-body or multi-body simulation, and then you can make it fit. And if this doesn't really work, then you have a general problem, but you would also have it in your workshop. And what you then have to do is make a cooling and clamping simulation and really bend it open or clamp the additional part in. And we can also do this. Okay, in this case, the deformation, which is quite small from the first step, doesn't really matter. So we can simply add the perfect CAD geometry, the meshed CAD geometry into this model, give it the material definition, and then we add the two robots that we want to have here. And now we can simply drag and drop the trajectories that we created just a couple of minutes ago. And yeah, do the same stuff again. And have then the same model, but not on perfect CAD, but considering also a pre-state, what we call pre-state step, where you have already deformed geometries. So I will skip over creating the geometries here because I think you already got the point. Okay, so then in the end, let's hop back to the original result. We will end up with this one. So you have residual heat from the previous step, and it is already deformed when we look here at the start of this simulation, and everything that happens after this will add up to the deformation. So now I have rebuilt my original problem. What I'm going to do with this is really the question. So Simufact Welding is basically a virtual test facility where you can conduct several, you can simply make a lot of copies of each and the same model. For instance, you can simply change the weld succession. You can also reverse them all. You can also reverse the welding direction of each particular weld line. You can also get rid of the robots and do everything with one robot. This was actually one variant that the customer considered because tandem welding has a lot of advantages when it comes to productivity, but it also adds up a lot of energy at the same time, and this might also caused this problem here with this pin. So they also did a variation where they only use one robot, which means only one weld line can be done at the same time. And you can also add certain boundary conditions to look if the entire structure behaves differently. And here is one, let's call it silly idea that they also wanted us to test. And this is not really using different welding successions or different heat inputs. But if we know the deformation here, why not use this and simply pre-bend this geometry? Because you will always, in this particular geometry, you will always have these very long weld lines. And there is nothing on the world that can change the fact that they will shrink during cooling, and they will always tend to, lift this pin a little bit up when once they're cooling. Of course, you can also start from here to here, but you still have a shrinkage along this lateral direction. So why not pre-bend them? And you can simply do this by use a copy of the welding simulation and make a cooling and clamping simulation out of it. Then all the robots are gone because it's not a welding simulation anymore. And then you can add additional boundary conditions. And in this case, we wanted to bend both the corpus pin plate tube and the reinforcement plate. And to do this, they are already connected via what is called local joints. They represent tack welds if you want. And then we are going to add an additional boundary condition, which is called clamping. And this is what they really are. They are solids, numerical solids that have a certain stiffness, so a virtual spring attached to them. They can also have stiffness and some sort of force if they would represent something like an hydraulic press. And they can also be something like a moving clamp, which is a very big hydraulic press that basically bends everything. And this is what we are going to use here. You can give them a start and an end time. In my case, I want a clamp, however it is shaped, to be moved from 0 to 5 seconds into the welding, into calculation time, from its start position up to 12 millimeters. And then you simply create a geometry and attach it to surface here. And then this is what this geometry is going to do. It will go from here to here in the direction which is depicted here by this arrow and move 12 millimeters downward, like this. And since we still have this fixing here, the entire structure will be bended around this fixture. Of course, in order to do this correctly, we need to add additional hydraulic presses, if you want, and position them properly, like here. Here, and on the other side. And then they are going to perform basically this movement, and they will push everything down that is in contact with these clamps. And this is what we have done here. This is the particular model with finished results already with residual energy. And let's show the boundary conditions. And this is a very small simulation that takes only a couple of minutes. And then our part is pre-bended, and it gets pre-bended to about 17 millimeter. And then again, we make a copy of this and add the weld lines, and then we end up with this model here, which is the entire suspension arm in pre-bended condition, and then we are going to weld along them. And we also flipped the direction here of the welding and see if this also benefits. Okay, let's jump to the result because I have to look at the time. So this is the final deformation of the pre-bended version of this suspension arm problem. So let's close all the other windows and compare this to the very first one that we had. So this is essentially the difference between the two variants. In order to really see which one is better, you can already see that the second one is much better, but we also have all sorts of result inspection. For instance, if we look at the original version, where is it? Here is it. We can do something that is called shape comparison. And to do this, we select a certain part that we want to compare and compare it to either scanned data. In this case, I have only the original CAD geometry and can compare it to each other. Here you see the red one is what comes out of the simulation, and this is the net shape where it is supposed to be according to the CAD data. You can also plot difference here, the surface deviation, but you pretty much see it also without colored contours. And we can also do the same one here. And we actually see that we, in this case, compensated much better, but we kind of compensated it. So maybe pre-bending of 12 millimeters was actually a little bit too much. because now it is pointing into the wrong direction or in the opposite direction. There is no correct direction. Okay, so this is how you can really set up and calculate very fast this kind of problem. I think you saw that it is pretty easy to set up this type of simulation in Simufact Welding. It's essentially clicking on entities or dragging and dropping material in predefined containers. And you have all sorts of model check that will help you to set up models. And we also have all sorts of result inspections. For instance, we can also look at certain results locally. And it also changes when we change the result value. By the way, I skipped a little bit over the result values. So sorry for that. I will do this now. So the result basically of this thermomechanically coupled simulation is not only temperature distribution and deformations, but you also get all sorts of stress information, equivalent stresses, but also the stresses in all directions, also mean normal stress or principal stresses. And we also display effective strains or also elastic strains. And in this particular case, the customer also considered phase transformation. So one of the informations that you can get from this simulation is also the distribution of phases like martensite, bainite, perlite, and so on. All right, so far from my side, let's hop back into the presentation. Well, I hope I was able to show you the ease of use and the look and feel of Simufact Welding GUI. Before we end this webinar, let me point out that we will have our last webinar next week on Tuesday. My colleague Pavel Kazan will dive a little bit deeper into this matter and will also answer you some technical questions, and he will also give you an outlook of what structural welding simulations may or will become in the future. We are talking really about things like automation and implementing this kind of simulation approach in an automated simulation workflow. All right. Then thank you very much for your attention. And if you have additional questions, please contact my colleague, Dr. Ingo Hahn.